Good day. For those of you who do not know us, we're the instructional staff for EC 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to describe the binary search algorithm. So, in this topic, we are going to describe the binary search, and we're going to do this first in terms of that familiar high-low game you've already played. We will then implement the binary search for an array of a given capacity. We will consider the conditions necessary to stop looping, and to do this, we will be looking at different cases. Now, suppose that an array is sorted and you'd like to find an entry in that array. You could, of course, use a linear search from the previous topic. A linear search is actually always necessary if the array is not sorted, for if the entry you're looking for may be anywhere, you need to check every single entry in the array. Question: can we speed this up if the array is sorted? Like, let's say, for example, you were referring to the index of a book and you had to find page 147. Well, if the book was 308 pages long, would you start to find page 147 by beginning at page 1? Probably not. You'd probably open the book to approximately the middle. Now, remember the high-low game. Let's suppose that your friend thought of a number between 0 and 99 and you had to guess that number. Alright, how about guessing 0 plus 99 divided by 2? And here we are using integer rounding. So 99 divided by 2 is equal to 49. In the off chance you're correct, great. If your friend says low, you're too low, and so your next guess is going to be, well, 49 is the wrong answer, so it has to be somewhere between 50 and 99. Let's pick the midpoint between 50 and 99, and that happens to be 74. And we'll carry on playing the game. If your friend says high, again, you're too high, so your next guess, well, now you're restricted to values between 0 and 48. So let's pick the midpoint, and 0 plus 48 divided by 2 is 24. And at this point, we can carry on the game. Again, remember we're using integer division here. So if you have a fractional component after the division is performed, the fractional component is discarded. Now, can we use this strategy for searching a sorted array? Let's suppose that we can implement this strategy, which we'll look at in the next few slides. In this case, the function declaration for a binary search would be equivalent to that of a linear search. We have an array, it has a capacity, and we are searching for a specific value. Alright, suppose we're searching an array with capacity 100 for this very specific value, 9,237.1. Now, the value could potentially be anywhere between index 0 and index 99. For if the capacity is 100, the indices run from 0 to 99. Alright, let's play the same game. Let's calculate the average of the two end points, the two indices, and 0 plus 99 divided by 2 is 49. Let's check entry 49. Alright, in the off chance that array entry 49 equals the value we're looking for, great, we have found it. However, chances are this is not the case. If the array entry at index 49 is less than the number we're searching for, then we're too low, and this means that the value we're searching for, if it even exists in the array, is somewhere between indices 50 and 99. Consequently, With our next search, we will once again calculate the average of these two endpoints and search entry or index 74. The only other possibility is that the entry at index 49 is greater than what we're searching for. Consequently, we are too high, so therefore we should restrict our searching now from indices 0 to 48, because again, the object we're looking for is not in index 49, so we are restricted now from 0 to 48. With our next guess, once again, we will inspect the average of these two endpoints. So 0 plus 48 divided by 2 is 24. All right, so let's start authoring our binary search algorithm. Now, the very first thing we're going to do is make sure that the array is sorted. In a previous topic, we wrote a function to return capacity if the array we are checking is sorted. Otherwise, it would return an index less than capacity. All right, now why are we doing this? Well, first of all, we want to make sure that at least while we're testing our binary search, that we're going to be testing it on an array that is actually sorted. Otherwise, we're going to run into trouble. For example, if you had a book that was 306 pages and you were checking to try to find page 146, well, if someone ripped out that page and inserted it after page 209, you're going to have some problems finding it. Okay, so this is just going to be a temporary check to make sure that at least while we're testing our function, that the array is indeed sorted. Next, we're going to have two local variables. The lowest possible index in which the entry could be, which will start at index 0, and the largest possible index where the object could be, which will be capacity minus 1. Now, we are going to have some sort of loop because we will be performing some actions while some condition is true. We don't really know right now what the conditions are, and therefore we're just going to not include the condition right now, but it's going to have to be a while loop. It can't be a for loop because we don't know how often we will have to iterate. Now, the first thing we will do is calculate the average of the lower and upper indices. So this is going to be the index at which we will inspect the array. Next, we will check if the entry at that average index equals our value. If it does equal the value we are searching for, then we will return to the user this index indicating that yes, we have found it and it is found at this index. Now, if the entry at the average index is too small, that means we have to carry on searching above this index. So we will set the lower index to be this average plus 1. So for example, if originally the lower index was 0, the upper index was 99, the average would be 49. So at this point, lower index would be updated to be 50, because we would now carry on searching from index 50 through 99. Otherwise, there's only one other possibility, and that is that the entry at the average index is too large, which means we have to continue searching below the average index. So we will update the average index to be the upper index to be the average minus 1. So once again, if lower index was 0, upper index was 99, and the value at index 49 was too large, we would carry on searching from 0 to 48. All right, so now comes the most interesting question. When do we stop searching? Well, let's think about this. So the question is, what is the necessary condition for the while loop to continue iterating? Well, actually, if the object or the value we are searching for is actually in the array, no halting condition is necessary because we are guaranteed to find that entry. Why is that true? Well, it's true for the exact same reason that if your friend asks you to guess a number from 0 to 99 and you use the algorithm as we described, you're guaranteed to find that number. So, if we are searching for something that's guaranteed to be in the array, we could just have the condition while true. Now, what if we're searching for a value that is not found in the array? Well, with every single iteration of the loop where we don't find the value, one of two things will happen. Either the value of lower index will be increasing, or the value of upper index will be decreasing. So consequently, pretty soon, lower index will be very close to or equal to upper index. So let's consider the various possible cases. Suppose that at any one step, it happens that lower index equals upper index while we were performing a search. Well, if this is true, then the average index will be equal to this value. And so if the entry at the average index is less than the value we're searching for, we will reduce upper index by 1. So now upper index will be equal to lower index minus 1. And if the entry or the value we are searching for is less than the entry at the average, then lower index will now be set to upper index plus 1. In both cases, lower index is now larger than upper index. Okay. Let's look at another possibility. Suppose that lower index is 7 and upper index is 8. Or more generally, let's say that lower index is 1 less than the upper index. Again, if you work out C++'s arithmetic, if you add n plus n plus 1 and divide that by 2, you will get n. So in this case, the average index must equal the lower index value. So if the entry at the average index is less than the value we're searching for, upper index will be updated to now equal lower index minus 1. If the entry at the average index is greater than the value, then lower index will be updated to be what ends up being the current value of upper index. So in the first case, lower index is greater than upper index, while in the second case, we're back to case 1. In the first case, we're guaranteed the object we're looking for is not in the array. In the second case, we'll go back to case 1 to determine whether or not the object is actually stored at what is initially here at index upper index. Now, here's case 3. Let us assume that we have a situation such as lower index being 8 and upper index being 10. So the difference between the lower and upper indices is 2. Well, in this case, the average index is going to be the value in between these two indices. So if the lower index was 8, upper index was 10, the average will be 9. So now, in either case, if the entry at this average index is less than the value, upper index will be reassigned to be the current value of lower index. And if the entry at this average index is greater than what we're searching for, then lower index will be updated to be the current value of upper index. In both cases, we jump back to case 1, and if the entry is not at that new location, then the object is not in the array. Thus, it seems we should stop looping as soon as the lower index is greater than the upper index. So this is what our loop condition should look like. While lower index is less than or equal to upper index, we keep on finding the average index and update accordingly. If this loop halts, that means we have not found the entry, so we will return capacity. You will recall that for searching algorithms, if the value we are searching for is found in the array, we will return the index at which that entry, the value, was found. That is, we will return a value between 0 and capacity minus 1. If we did not find the value we are searching for, we will return capacity to let the user know that we did not find what we were looking for. All right, so here is our binary search function, and here's our condition, and if that condition ever fails, we will stop the for loop and return capacity. Okay. Now, here is a test that you could run to see whether or not the binary search function works correctly. So what I've done here is I've created an array of capacity 5 that contains the entries 0, 1.2, 1.5, 2.7, and 4.6. So I'm going to have a loop here where k goes from 0 to 10 times capacity, and then x will be assigned k divided by 10. So what I'm going to do is have x being assigned the values 0, 0.1, 0.2, 0.3, all the way up to 5.0. Every single time I will check, is the value 0.0, 0.1, etc., etc. in the array using a binary search. I'll check to make sure that whatever binary search returns is greater than or equal to 0 and less than or equal to the capacity of the array. Now, if the value returned by binary search is equal to capacity, I will just indicate that x is not found. Otherwise, I will indicate that x is at data with the specified index, and I will also print out what is at that index. All right, let's check that out. If we run this test, here's the output. So we notice that for each value that is in the array, it was found at the appropriate location. 0 was found at index 0, 1.2 was found at index 1, 1.5 is found at index 2, 2.5 is found at index 3, and 4.6 is found at index 4. For every other value between 0 and 5, the value was not found, which is exactly what we expect. All right, so it seems like our binary search algorithm is working. Maybe. Now, did any of you notice a possible weakness in the test we ran? Well, if you take a look here, we never actually search for a value less than the first entry of the array, because when k is equal to 0, x equals 0. So we never actually test for something that is not less than the first entry of the array. Well, the easiest way to fix this is just to make the first entry of the array 0.3. Consequently, in the loop, we should find that neither 0, 0.1, nor 0.2 are found in the array. Not a problem. However, on my computer, if I now run this test, I don't get an assertion error. I get a segmentation fault, which means I tried to access memory that I could not access. Now, why is that? So to see how we got to this point, suppose both lower index and upper index both equal 0. In that case, the average index will also be initialized with a value 0. And if the entry at index 0 is greater than the value we are searching for, then upper index is assigned the value 0 minus 1. Problem: standard size t is unsigned. So 0 minus 1 is going to cause a carry. In other words, it will loop around to being the largest possible value that can be stored in a local variable of type standard size t, which happens to be a very large number. It's either 2 to the 32 minus 1 on a 32-bit computer or 2 to the 64 minus 1 on a 64-bit computer. How do we test for this? Well, notice that the maximum value that can be stored in standard size t is some value that's going to be greater than or equal to the capacity of the array. Thus, if upper index is equal to this maximum possible value, then upper index must also be greater than or equal to the capacity. So we can deduce that upper index has this maximum value if upper index is ever assigned a value greater than or equal to capacity, because you'll recall that in our algorithm, upper index begins at capacity minus 1, and our algorithm only ever decrements the value of upper index. Okay, thus we now have two conditions under which we should not continue iterating the while loop. We should not continue iterating the while loop if either lower index is greater than upper index or upper index is greater than or equal to the capacity. Consequently, we should continue iterating the while loop as long as both of these conditions are false. So it is false that lower index is greater than or equal to upper index, and it is false that upper index is greater than or equal to the capacity. Thus, we should continue if both of these conditions are true. That is, lower index is less than or equal to upper index, and upper index is less than capacity. You'll notice that this is correct because lower index being greater than upper index being false is the same as saying lower index is less than or equal to upper index being true. Similarly, upper index being greater than or equal to capacity being false is the same as saying upper index is less than capacity is true. All right, so now we have our complete and working implementation. All we need to do is add the second logical condition that upper index must also always be less than capacity for us to continue iterating this loop. If this condition is ever false, then the while loop will stop and we will return capacity, indicating that we did not find that particular value in the array. Now, you might wonder, what type of error is this? What caused us to have to check if upper index was equal to the maximum possible value that something of type standard size t could take? Well, this was actually not a problem with the binary search algorithm. The algorithm itself assumes that upper index can take on the value -1, and if it could take on the value -1, the implementation of a binary search would work as expected. However, it is because we used a type that was unsigned that this error appears. Such an error is called a semantic error. We are expecting integer arithmetic to work as it does in the real world. Unfortunately, this is not what happens when we are working with unsigned integers in C++. Don't worry too much about semantic errors at this point, but essentially this is an issue when you are using the tools of the programming language incorrectly. Now, here's also another observation. The fix we just made also fixes a second mistake which you may not have noticed. If you tried to run the original binary search we wrote on an array with capacity 0, well, if the capacity of the array is 0, that means that the array does not contain any entries, and therefore any value we are searching for cannot be in that array, and therefore we expect 0 to be returned. The problem is the initial value of upper limit is 0 minus 1, which is the maximum value of standard size t. Thus, we've actually taken care of two weaknesses with one fix. Also, I'm pointing this out to emphasize that you do have to test all possible bounds. So, an array with capacity 5, 6, 7, but also an array of capacity 0. Now, there is one little problem with our test. The test that we wrote actually requires us to inspect the output visually. We have to make sure that all the entries are accounted for. Question is, can we write a test that does not require us to inspect the output? Well, here's one such test. So again, I have the same array I'm searching. However, now I'm going to have a local variable found count, which is initialized to 0. Once again, I will search through the array. However, now if I find an index that is not equal to the capacity, I will make sure that the value at that index is equal to the value of x that we were searching for. If the value at that index is not equal to what we were searching for, the assertion will fail and we'll have an error. If that assertion passes, then we have correctly found the value at that location, and we will increment the found count by 1. Consequently, once we have searched through the entire array, I'm going to make sure that we have found as many things and no more and no less than are currently in the array. And again, if we found fewer than the number of things that are in the array or more than the number of things that were in the array, then this assertion also would fail. So this test, if it passes, does nothing. This test, if something is wrong, will have an assertion error displayed to the screen. Now, there is a small weakness here. If there is a duplicate entry in the array, this test will fail. So we may have to be a little bit more careful. But nevertheless, this is a test that does not require you to explicitly examine the output. Instead, you simply see whether or not executing this program results in an assertion error or not. All right. Now, here's a question. Suppose we do a binary search on an array of capacity n. What is the maximum number of entries of that array that we must inspect before we know for sure whether or not that value appears in the array or not? Of course, this value, the maximum number of entries we must search, will be increasing as the capacity of the array increases. But how quickly does it increase? Well, let's just take an example. Suppose we have an array of capacity 127. Basically, this means we have to search the entries from index 0 to 126. That is, we have to search 127 entries. Now, at the average of these indices, we have 63. So if it is not at index 63, we must continue searching from index 0 to 62 or 64 to 126, based on the relative value. In both cases, we are now restricted to searching only 63 entries, not 127 entries. Now, in the first case, we're going to check index 31. If it's not there, then we're reduced to either searching from indices 0 to 30 or 32 to 62. In the second case, if it is not at the average, which is 95, we will carry on searching from 64 to 94 or 96 to 126. In all four cases, we are now restricted to searching only 31 entries. Now, you'll notice that these values are 2 to the 7 minus 1, which is 127, 2 to the 6 minus 1, which is 63, 2 to the 5 minus 1, which is 31. You may correctly deduce that this pattern will continue. If we keep on performing the binary search, we will restrict ourselves to needing to look only at 15 entries, then 7 entries, then 3, and then 1. And having inspected that last entry, we will know whether or not the value is in the array or not. Okay. Now, in your course on algorithms and data structures, you will actually prove that a binary search will inspect no more than log base 2 of n plus 1 entries of the array, where n is the capacity of the array. Now, if you had to perform a linear search on an array of capacity 1 million, this may actually require you to search all 1 million entries. A binary search on a sorted array of capacity 1 million will require you to perform no more than log base 2 of a million plus 1 inspections, which is 20.9, and so therefore you are required to inspect no more than 20 entries of the array before you are guaranteed that you know whether or not that value is in the array or not, and if it is in the array, you will know which index it is in. So following this topic, you now understand how to implement a binary search in C++. You are aware that you must thoroughly test your implementation to ensure that you have not missed any edge cases. You also understand that there may be issues with the implementation of the algorithm as described. In our case, we had a semantic issue. The description of the binary search algorithm was correct. However, we were using an unsigned integer data type, so when we calculated 0 minus 1, we didn't get the value -1, but rather we got the maximum possible value of standard size t. That is, we had a carry. So we had to deal with this separately. You're also aware that a binary search is relatively fast compared to a linear search, but for the binary search to work, the array must be sorted. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!